Hello everyone, as our host said, I'm Lefteris. I'm a research scientist at Misten Labs, and I'm going to present our latest protocol, Walrus, which focuses on decentralized storage. Why should you care about decentralized storage? In general, if you look into storage, you're going to see that around 50% of the cost of most cloud services is going to storage. So storage is very important. And with machine learning, IoT, big data, it's just increasing and increasing as a cost. And here we are at Web3, where even using cloud storage is not really something that we should be doing, right? We want to build apps which need to achieve decentralization. And for this, we need to actually use some Web3 form and get decentralization. We cannot simply trust a centralized service. And just putting data on chain is not only extremely costly, but also quite wasteful. You don't really want to have 100x, 1000x replication in every single full node for data that are just going to be read like a video or a picture. This is really to be used for actual state that we want to compute on. And the situation currently, both for Web2 and Web3, and Web2 can actually use Web3 decentralized storage, is that we're using cloud services which are limited in resiliency. They have single points of failure, like Google Drive kind of failed yesterday, right? You can get censorship if someone decides that the data that you are putting there is not to be read or accessed. We have vendor lock-in. If anyone has tried to deploy stuff on cloud storage, they know how hard it is to move to another, maybe cheaper, maybe better solution. And in general, you get weak integrity. This means that the data that you are accessing, you don't really know if they're the actual data that whoever put there meant to do. You just download them and hope that this URL link that you're using actually hosts the exact same data and is not altered. But you have no way of actually knowing it and knowing that it actually came from who you want it to come from. Walrus wants to address all of these problems. It operates a decentralized storage network that achieves high resiliency, credible neutrality, and robust access. What is Walrus? Walrus is working in the classic model that we have in also most proof-of-stake blockchains of Byzantine fault tolerance, the classic 2/3. And its goal is to store large blobs. We're talking about hundreds kilobytes, a few megabytes, not really small data, but quite large, even gigabytes. It provides efficient reads and writes and provides verifiable availability. If you put some data on Walrus, you have a proof that Walrus will store it and have it available for the amount of time that you requested. All this comes with quite low storage overhead, and it's permissionless. We have storage nodes that are going to rotate in a committee fashion, such that if some nodes don't want to participate anymore, they can give the responsibility of storing data to some new nodes. So it's permissionless and nodes can participate as they wish. And for that, we provide incentives in order to get continued storage. What Walrus is not. Walrus is not a CDN. We're not having a goal of very high scale, very low latency access on Walrus. You can build a CDN along with Walrus using Walrus for the robustness and the availability. It's not a database. You cannot just put your payroll on Walrus and ask SQL queries. You can use Walrus for a backup in order to make sure that your data is always available. And it does not implement consensus or execution. Walrus really focuses on building a decentralized storage system and avoids reinventing the wheel in order to build a full L1, a full virtual machine to run a full smart contract platform. For that, we use existing solutions like the Sui blockchain. What is the core of Walrus? The core of Walrus is our novel encoding scheme called RESTAF encoding. It provides low overhead, efficient recovery. This means that nodes can recover the data that they're supposed to hold by only communicating a small amount of data and not having to reconstruct the whole lost data in order to get only the small subset that they are supposed to be storing. It has consistency checks. This means that if I read some data from Walrus, I know that everyone else will read the exact same data, or I will detect that this data has been corrupted by its initial source and everyone else will also know that this data has been corrupted. So we can all agree on whether data is correct or not and whether it's available or not. And the key property of REST staff encoding is that it provides write completeness. Write completeness means that if the initial writer didn't manage to send all the parts of the data to every single storage node, it doesn't mean that those nodes are going to now disappear. They can realize that something went wrong and ask their peer nodes to recover the data so that everyone holds a piece. This is very critical when we do epoch changes, when we move committees, so that we know that everyone can recover the data that they've lost. And it's also critical for incentives, so that we can check anyone on whether they're actually storing the data they're supposed to. So, on a high level, getting a bit out of the encoding, how does Walrus work? Walrus has clients, anyone that wants to write some data. Those clients store and read blobs. We can have optional publishers. The publishers are basically services that peer with the clients so that the clients don't have to know about Walrus or about encoding, decoding, all these complex things. Instead, they can simply ask a publisher node to do all this work for them. And we also can have optional caches that hold hot copies of the data so that you can interact with like any Web2 service you like and directly read and write. If the cache evicts the data, it can always go on Walrus and recover it in case it's being asked again. The other thing that we have is storage nodes. Storage nodes are basically almost the same as validators, but they have much more storage and don't need so much compute. And we assume the classic 2/3 of them to be correct at any point in time. And finally, we have smart contracts. These are not on Walrus. We use the Sui blockchain in order to implement the whole logic of Walrus, and we use it for coordination. So a typical interaction of Walrus is these three things: storage nodes, the contract, and the Walrus client. The client is going to talk to the contract and say, I want to obtain a storage resource. I want to get 1 GB of storage for a month. The Walrus contract checks that there is available storage on the storage nodes and gives the storage resource. The resource can be then sold, split, traded, whatever you like to do with it. It's programmable. But the normal thing to do is to register a blob on the storage resource. So you're going to say, OK, I want this data to be stored on my gigabyte of data. The contract checks that this has been correctly created and informs the storage nodes that there is a blob being registered. Now you need to store some data. That's what it tells the storage nodes. The Walrus client then encodes the data and sends different parts to every storage node, which are committed through a milk tree. And as a result, every storage node can check that they receive the data that they're supposed to. When they check, they send back a signature to the client saying, OK, I'm good. I will be storing your data for the 1 month that you bought. The client collects 2f+1 of those. This is an availability certificate and puts its post on the contract. So it's on chain now. An agreement between the Walrus contract and the client that Walrus is going to store this specific blob ID for this specific time. It informs every storage node that this has happened, so now the storage node know that they should not delete the data. And also, some storage nodes, here you see the right one, might be notified that they didn't really get the data, and as a result, they can use a recovery procedures with the rest of the storage nodes to recover the part that they were missing without having to talk to the client. The client can basically go away, disappear, delete the local data the moment they have seen the certificate uploaded correctly on the contract. Reading is much simpler. The client simply goes to the storage node and asks them, oh, this is the blob ID you promised to be storing. Here is a proof on chain. And as a result, I want you to give me the part that you're supposed to be holding. Then they wait for f+1 or 2f+1 responses. This is a parameter depending on how robust we want the challenge and the incentives to be. When they receive those responses, they decode the blob. Then they re-encode the blob and check that they retrieve the same blob ID as the one posted. If this is true, they know that the data has been intact and correctly encoded by the client, so they read correctly. If they don't get the same blob ID, then they know that the initial source node has corrupted the data, has done the encoding the wrong way, so they exit saying that this is corrupted, and they also know that anyone that will ever try to read the data will also see the same error. So they know that there is agreement. Right? So this is the high level of the Walrus, and you can use it for all the things you can imagine, right? The more obvious thing is you can use it to have media for your applications or NFTs. You can now implement social media and put videos and have them on-chain. They're not really on-chain copied on the validator, they're on Walrus. You can build decentralized websites, and we have one called Walrus sites that you can check out. This means that there is a website that is uploaded on Walrus so that you can access it with a simple HTTP request, but you can actually check that it has been received the way intended by its source. It has a hash, it has a commitment. As a result, you get data integrity. You can do the same with anything else. You can do it with datasets, with model weights, with proofs of correct training. Anything can be uploaded on Walrus. And the cool thing here is that you always know that you are receiving the data as intended by its original source. It has not been censored or altered. You can, of course, use it for archival, for your blockchain history, for websites like the Internet Archive, or we have actually the archive of papers that you can put on Walrus as a robust and censorship-resistant way to upload things. And you can also use it for data availability, for L2s, whether on Ethereum or anywhere else, and it's actually quite cheaper than existing solutions. Now, let's see a bit how Walrus actually works. But to get the idea, we're going to start with like some very simple examples of how would you build a decentralized storage system. The simplest one is we're going to just fully replicate the data, right? We have like a blob here, and we're going to just copy it twice and give it to 3 different storage nodes. Now we know that we have robustness because as long as one out of those 3 is available and replies, we're going to always have access to the data. Very simple. This is a very simple solution, and this is actually very attractive. You can easily implement it. You can explain it to a bachelor's degree student, and they can implement it. The other cool thing with full replication is that you don't need to coordinate with many storage nodes. You just find one, ask them for the data. If they're nice, they're going to give it back to you. So very simple to also read. And the same goes for recovery. You don't really need to run any coordination to recover data if you're doing full replication. You just need to find a copy, read whatever you lost, and you're good. You're golden. So very simple, very intuitive, but very costly. On the one hand, if you want to get like really strong security, like the same security that we're getting with Walrus or any other encoding scheme, you're going to need around 25 copies. This is a lot of data. If we're talking for like 1 gigabyte, 10 gigabytes, like 1 petabyte of total storage, 25x is quite wasteful. Reading and writing, in the worst case where you're trying to find the data, but there is a good number of nodes that are malicious, unresponsive, slow, can result to reading basically almost every single node until you hit one that's actually honest and did not corrupt the data. So that's also very costly, and that also carries down to epoch changes. If nodes want to disappear, then someone else needs to come and pick it up from them, and to come, they need to actually figure out where to find the data, and then can be asking left or right, because fault tolerance is not really in the protocol, it's just on the replication. And a thing that is not super important right now, but we actually have it on Walrus, is the fact that you can do asynchronous challenges, which means that you don't need to rely on your network being really good in order to make sure that nodes are not simply deleting data, then copying it from their friend when you ask if they have them. But you can run a much more robust challenge protocol. Okay, so this is full replication, quite intuitive, but costly. How can we simplify it? Well, the other solution that has been proposed along decentralized storage is the use of erasure codes. How does this work? Well, you get your initial data and you split it into pieces. We're going to call them f+1 pieces, meaning that up to f of those nodes can disappear. And you have those f+1 pieces, and what you do is you encode using something like Reed-Solomon encoding, which is what we're using also in Walrus, into 3 f+1 data. So basically you triple the amount of data you have, but then any set of f+1 recovers the data. You don't need to go to get specific. You can get any of them, and they will all give you the exact same data. This is very cool. This slashes the overhead to the absolute limit, really. You only do 3x replication to get 1/3 fault tolerance, right? This is very low. You can have security of 10 to the minus 12 accessing the data just by copying 3 times the data which means that if you have a lot of storage nodes, the amount of data each one stores is extremely small. This also means that reading and writing really is equal to the cost of downloading the blob. Right? Again, really cool. You just ask around. Worst case, you will ask everyone. You will retrieve all the data. You just paid 3x more. Most of the time, you're not going to even pay that. You're going to pay the exact cost of the data. And it's really secure. On the negatives now, is that it needs to actually find f+1 nodes to get those pieces. So it can be a bit slower and a bit more involved to actually do it correctly. Recovery of data still needs to download the full data, pick the piece that you are missing, and delete the rest. So this is quite costly, and if you want to change epochs frequently, it can result in a lot of bytes being shifted on the network at specific points in time when data is being, when the epoch is changing. And as a result, the epoch change also requires, worst case, downloading every single node that needs to get new data, downloading the full blob, getting their piece, because we don't want to coordinate with a single recovery, which is a trust assumption. And again, this also does not support asynchronous challenges. So let's get into how red stuff works. Red stuff takes the encoding one step further and actually does it in 2 dimensions. So we have the blob and we split it into 2f+1 by f+1 pieces. This different threshold is what allows us to have write completeness, really. And now we got on the x-axis, we have 2f+1 pieces. We extended by 50% to go to 3f+1 pieces. On the y-axis, we have f+1 pieces. We extended 3x to get, again, 3f+1 pieces. And then what we say is that every row is called a primary sliver of the data. It has n symbols, which are really small. They're order of blob over n squared. And we have n symbols primary, and its column is a secondary sliver. And then we go, and every storage node gets 1 primary, 1 secondary sliver. So the first one will get 1, 1. The second one will get 2, 2. Third, 3, 3. Fourth, 4, 4. Right? So everyone, again, gets only 1 over n of the data, the same as the previous protocol. But they are much more structured in a way that will allow us to do very efficient recovery. And this is really the key property that makes red stuff so unique, the fact that it's self-healing. The protocol can recover lost data by communicating only the amount of data that has been lost without any central coordination, right? So we have this when we run a write protocol on red stuff. Each node has its row and its column. Now let's say that node 4 wasn't very responsive at this point in time, so it didn't get the data. And also we have faults. So node 2 here just decides to disappear. They're like, I'm not going to participate in this thing. Thank you very much for the money for now. How is node 4 going to recover the data? Well, if you notice, every primary sliver intersects with every secondary sliver at 1 symbol. As a result, node 1 has 1 symbol that node 4 wants on the primary and 1 symbol that node 4 wants on the secondary. So it can send those 2 symbols to node 4. Node 3 can do the same. It has different symbols that node 4 wants, right? So now node 4 managed to get 4 symbols. Because on the y-axis, on the secondary sliver, we had a low threshold of f+1 encoding, this is enough. You have 2 out of 4. As a result, you can recover the full secondary sliver. When recovering the secondary sliver, you actually get another symbol that you were needing, the 4, 4 symbol there. This increases the number of symbols you have on the primary sliver, and in this example, the node 4 has all it needs. In higher numbers of n, you need to communicate a bit more, but eventually you're going to get enough symbols, 2f+1, because that's the assumption of honest nodes, that will allow you to recover your primary sliver as well. As a result, we just communicate the amount of data that was lost, right? We had lost like 8 symbols, we communicated 4, and we recovered the other 4. So this is why red stuff is cool. It provides low overhead, 4, 4, and 5x. Like it's a bit higher than red stuff because of the 1D encoding because of the 2 dimensions, but still constant size. It doesn't increase with the number of nodes. It's really good because as you get more storage node, each storage node needs to store less data per blob. Reading and writing the same as in 1D, is order of the blob. So you just read the amount of data you want to receive. It's secure. It supports asynchronous challenges, meaning that you don't need to rely on the network synchrony to make sure that nodes hold the data they're supposed to. And it provides self-healing recovery. This means that you only require an order of blob over n bandwidth to recover lost data. This allows for a non-blocking epoch change that has self-healing and is very efficient. On the cons, you need to get 2 f+1 replies or f+1 replies, depending if you want asynchronous challenge or not, to read the data instead of just going to 1. But that's why we have caches, because then in the cache you can just get them, and in the worst case that it's not there, you need to do the communication. So I'm going to skip on the epoch change and the storage at the station because I have 1 minute left. But you can check the slides or the paper and just end up with the fact that Walrus storage is a very cool new decentralized storage network. It's lean, it's responsive, it's robust. It's lean because we built it to do one thing, decentralized storage. It doesn't run consensus, it doesn't run smart contracts. These are the jobs of different tools. As a result, it's laser-eyed on its focus and makes it very efficient. Very responsive because of how red stuff works, and very robust, having the self-healing property which allows recovery very quickly and very efficiently. So, thank you very much.
Thank you very much, Lefteris. And we are moving into Q&A. There are a lot of questions, and I sorted them by popularity. So the most popular question is, could you briefly outline how this compares to Filecoin?
Yeah, of course. So I would say that Filecoin has some pros and cons. On the pros of Filecoin is that it's more permissionless than Walrus. In Walrus, we need to have this committee, you need to set up the committee, and you rotate it once every 2 weeks right now. Whereas in Filecoin, the node that wants to upload data just decides how many copies it wants, gives them, and they're stored. If it wants more copies, it will make more deals and put them on. So this is much more permissionless. You come and go as fast as you like, but it needs coordination on the node to know how many copies it has around. It is quite hard to read from Filecoin because it relies on actually encrypting the data to do the proofs that the Filecoin consensus needs. So actually getting it out is quite costly and slow. And the Filecoin is really full replication, really is the first example that I had. You need to make a good amount of copies to have strong guarantees that it's there.
Okay, so second most popular question would be, do clients have to pay to retrieve big blobs of data? How do you prevent DOS DOS attacks on egress otherwise?
So currently they don't have to pay, but we're looking, and there is a rate limiting, of course, and it's not really the client, it's who uploads that usually pays in storage networks for the clients to read. But we plan to actually add some incentives also there if we see that there is a lot of load.
All right, third question. Are retrievals incentives? What happens if the storage node fails to serve it? Example, are they slashed?
Yes, so at epoch change, which I didn't have the time to describe, basically when a node wants to leave, another node needs to come. And if they actually efficiently transfer the data, so you just take your slivers and give them, then you both get paid. But if you are actually need to cause a recovery, this is going to create some slashing. That's the first one that already exists. And we're going to also have storage at the station and asynchronous incentives in the future that basically randomly check if you have some files, and if you don't, you're also going to be slashed.
Okay, we have 2 more minutes left, and the fourth most popular question is, why is the blockchain part necessary? Just registering file existence seems like a weak reason. Example, IPFS doesn't need it.
So the blockchain part is necessary for all the staking, for basically everything else other than uploading the data, right? That's why I'm saying that Walrus just uses a blockchain. So yeah, we need it for all the logic, and also our storage resources are programmable. So you can buy some storage, then resell it in a secondary market, split it, delete it, do whatever you want. And all this comes with incentives, which is really important in decentralized fashion. Otherwise, the previous two questions were exactly for that. You need incentives, and to do good incentives, you need the blockchain.
All right. Last question. Is it possible for me to somehow encrypt the data and/or give others permissions to retrieve it and end of
Yes, yes. We have another sister application to Walrus called Seal. You can see the joke on the names, which actually provides threshold encryption service and access control in order for you to use it and then upload on Walrus encrypted data. Of course, you can also do any key management service you want on your own. Walrus doesn't care. It's a blob, it's bytes.